Now we're going to move from discussing the deployment pipeline to discussing an architecture that's ideally suited for continuous deployment. That's the microservice architecture. So two pieces to this. One is what is it? And two, how does it cut down on coordination requirements? So a microservice architecture, it's actually an architectural style, is a collection of independently deployable processes. They're all packaged as services and they communicate only via messages. So in around 2002, Amazon instituted the following design rules. All teams will henceforth expose their data and functionality through service interfaces. Teams must communicate with each other through these interfaces. There will be no other form of inter-process communication, no direct linking, no direct reads of another team's data store, no shared memory, no backdoors. The only communication is via service interface calls over a network. So this gets modified a little bit when we start to talk about coordination. Uh, it doesn't matter which technology each service uses because all service interfaces are going to be through messages. So as long as your technologies support message passing, and all of them do, you can use whatever language you want, whatever tools you want, whatever libraries you want. And service interfaces must be designed to be externalizable. Most of them are not, but the potential is there. And this is the specification for what later became the microservice architecture. Amazon didn't call it the microservice architecture; they called it SOA done right. But later the term microservice architecture came in. So also Amazon has the two pizza rule. So the team should be no larger than can be fed with two pizzas. It's around 7. Uh, each microservice is responsible. Each microservice is the responsibility of one team. A team can manage multiple microservices, but each microservice belongs to only one team. And this means that the services are small. If you have a 7-person team, they're not going to build a 200,000 line service very quickly. It also means that intra-team, within the team, the bandwidth is high because there are a small number of people and they can coordinate quite easily and quite closely. Large systems are made up of many microservices. In a typical Amazon page, you might see as many as 140. That's just the external part of it. Services can have multiple instances, so the elasticity of the cloud will adjust the number of instances of each service to reflect the workload. Requests are routed through a load balancer for each service, and this leads to lots of load balancers and overhead for each request. Just a short digression into service-oriented architecture. The definition of microservice architecture sounds a lot like SOA. So what's the difference? And the difference is that SOA has a lot more things, but microservice architecture doesn't. SOA has an enterprise service bus. There are all these WSDL kinds of things. And fundamentally, each service may be under the control of a different organization. That's not true in microservice architecture. Everybody works for the same company that has it typically. You also have brokers, and there's just a whole infrastructure that got built on top of SOA that doesn't exist for microservice architecture. So each user request comes to one of the externalized services. It then gets passed off to other services through various service interfaces, and each service does a coherent type of thing. You can design this so the service depth is shallow, so there's a large fan out, but not very deep, or that it's deep, in which case you have a small fan out and more dependent services. So let's look at coordination decisions. So coordination can be made incrementally as the system evolves or built into the architecture. And microservice architecture either builds most coordination decisions into the architecture or delegates them to the team. So consequently, these kinds of decisions only need to be once for a system, not once per release. So the 7 decision categories that come from software architecture and practice are allocation of functionality, the coordination model, the data model, management of resources, mapping among architectural elements, binding time decisions, and technology choices. And we'll see that the only two categories that are left to be that need coordination as the system evolves are allocation responsibilities and the data model. Everything else is either delegated or decided by the architecture. So what I'm going to do is go through these categories one at a time and discuss how the architecture satisfies them or delegates them or requires coordination. So allocation of responsibilities, this is done as the system evolves. So this is no different than any other agile type of methodology. The development teams must coordinate somehow, and typically this happens at the beginning of each iteration, although I've seen models where the allocation responsibilities are done for iteration n+1 while the team is working on iteration n. But it happens close to when the actual coding is done. Coordination model, everything is done via asynchronous messages. What this means is that each service could, in principle, be deployed anywhere on the net. Of course, this would affect the latency dramatically, and so they tend not to be deployed so widely. And you have to manage state. When you have independent message passing processes, they don't share state. They don't, and so they don't share address space, and so state has to be managed in a particular way. So services can be stateful or stateless. Stateless services allow arbitrary creation of new instances for performance and availability. An instance fails, you create a new one. Nothing's lost. Instances get overloaded, you create a new one, send them messages, they can start work. They don't need to have state built into them. Stateful services don't require as much overhead. You don't have to send this because the stateless services have to get their state from somewhere. And so stateful services retain their state from one call to another. So it reduces the overhead. But it requires clients to communicate with the same instance because that's the one that has the state. So where do you keep the state? Well, if it's persistent state, you keep it in a database. And modern database management systems, relational database management systems at least, provide replication functionality. Some of the NoSQL systems may also be replicated. Others require manual replication at this point. Transient small amounts of state can be kept consistent across instances by using tools such as Memcached or Zookeeper. And so this is a little bit outside the rule that the services can't share state. Different instances of the same service can share state through essentially a state management coordination instance. And I'll talk about these in more detail. The important point at this point is that it's a limited amount of state. You're dealing with a meg or maybe less. Also, instances may cache state for performance reasons, which means that if you're going to bring down an instance, you have to purge a cache. And if you're spinning up an instance, you have to populate the things that it expects to get out of the cache. The data model is like the allocation of responsibilities. That requires coordination. Initially, when you define a schema, then you have to coordinate. Ideally, the schema never changes. They should be rare. You can do schema extensions. You can put new fields or new tables without a problem, but modifying existing data, existing schemas and the semantics of the various fields causes complications. NoSQL systems, again, have to require coordination over the semantics of the data. So in a NoSQL system, the schema is implicit rather than implicit, but it's still there. Resource management, each instance of a service can process a certain workload. And this could be expressed in terms of number of requests. It could be expressed in terms of resource requirements. And each client instance will require resources from the service to process its requests. And so in more sophisticated organizations, this is done automatically through service level agreements. A client contracts not to send more than a certain number of requests per unit time. The service contracts to be able to provide service for a certain number of requests. If you add up all the requests coming from the clients, and that's greater than the number of requests that the service can do, that it's agreed to, then you allocate a new instance of the service, and this can be done all automatically. Decisions about packaging modules into processes are delegated to the service development team. We'll talk about deployment later. Binding time. So part of the binding time is decided during the architecture. Others are delegated to the service development team. And technology choices are very explicitly delegated to the service development team. So to summarize, microservice architecture packages services as small independent processes. And the critical element of the other two critical elements of this, one is that each team makes its own technology choices. And so you don't need to coordinate over things like versions of libraries or even languages. There are microservice architecture where one service is done in a functional programming language such as Scala. We'll see this in our case study, and others are done in Java or C or some standard language. And so the second technology choice is that everything is done through messages. And because everything is done through messages, it doesn't matter which technologies you use.